Today I will discuss thermodynamic potentials. Thermodynamic potentials are state functions that, together with the corresponding equations of state, describe the equilibrium behavior of a system as a function of natural variables. The natural variables are a set of appropriate variables that allow to compute other state functions by partial differentiation of the thermodynamic potentials. Natural variables are pressure, volume, temperature, and entropy. Thermodynamic potentials are number 1 internal or intrinsic energy, number 2 Helmholtz function, number 3 enthalpy, number 4 Gibbs potential. Now first we will discuss internal or intrinsic energy, which is denoted by symbol U, capital U. When a system shows no mechanical energy but is still capable of doing work, it is said to possess internal energy or intrinsic energy. In an infinitesimal reversible process, change in this internal energy is given by the first law of thermodynamics as du is equal to dq minus dw. And from the second law of thermodynamics we have dq is equal to tds. Hence, du can be written as du is equal to tds minus pdv because dw is equal to pdv. Therefore, when entropy remains constant, that is ds is equal to 0, we will get du is equal to minus pdv. So from here we can write p in partial differential form as p is equal to minus del u over del v at constant s. Similarly, when volume remains constant, then dv is equal to 0 and we can write du is equal to tds. So t in partial differential form will be written as t is equal to del u over del s at constant volume v. Thus we see that just as the derivative of gravitational potential or other potentials given density of the corresponding field, the basic coordinates p and t are given by the derivatives of the internal energy. Hence, internal energy is considered as the first thermodynamic potential. Now we discuss Helmholtz free energy, which is also called Helmholtz function, represented by symbol capital F. On combining the first and second law, we have du is equal to tds minus tw. If we consider processes in which the system exchanges heat with the surroundings and maintains constant temperature, then we can write tds is equal to d of ts, and we can write du is equal to d of ts minus dw, or d of u minus ts is equal to minus dw, or df is equal to minus dw, where f represents the term u minus ts, and this is known as Helmholtz free energy or Helmholtz function. This depends upon the state of the substance, and also df is a perfect differential. Now df is equal to du minus d of ts equals du minus tds minus sdt, but du is equal to tds minus pdv. Therefore df is equal to tds minus pdv minus tds minus sdt. TDS cancels and we get df is equal to minus pdv minus sdt. Here t and v are independent variables. Now taking partial differentials of f, we get at constant temperature dt is equal to 0. So p equals minus del f over del v at constant t, and at constant volume dv is equal to 0. So we get s is equal to minus del f over del t at constant v. So here differential of f gives p and s, hence this becomes second thermodynamic potential. Now we discuss the third thermodynamic potential called enthalpy or total heat. It is represented by the symbol H. The total heat content of the system is known as enthalpy. It is mathematically written as H is equal to U plus PV. On differentiating it, we will get dH is equal to du plus pdv plus vdp, or dH is equal to tds minus pdv plus vdp. So here PdV cancels and we get dH is equal to TdS plus VdP. Hence if P is constant, that is dP is equal to 0, then we get T is equal to del H over del S at constant P, and if S is constant, then we will get ds is equal to 0 and V is equal to del H over del P at constant S. Thus T and V are given by the derivatives of S, so H is known as thermodynamic potential. Now we discuss the fourth potential, that is called Gibbs potential or Gibbs free energy, represented by capital letter G. From the definition of enthalpy, we have H is equal to U plus PV. Differentiating both sides, we will get dH is equal to du plus pdv plus vdp. Now putting the value of du here, we can write dH is equal to tds minus pdv plus pdv plus vdp. This becomes dH is equal to tds plus vdp. Now for isothermal and isobaric process, we will have TdS is equal to differential of Ts and Vdp is equal to 0. Therefore dH is equal to d of Ts plus 0, or dH minus d of Ts is equal to 0, or we can write d of H minus Ts is equal to 0. So here the bracketed quantity H minus Ts is constant because its differential is 0 in isothermal and isobaric process. This quantity is called Gibbs potential and is represented by capital G. So G is equal to H minus Ts. Putting the value of H here, H is equal to U plus PV, we can write G is equal to U plus PV minus Ts. Now differentiating both sides, we get dG is equal to du plus pdv plus vdp minus tds minus sdt, or we can write dg is equal to tds minus pdv plus vdp minus tds minus sdt. Here the bracketed term tds minus pdv is substituted in the place of du. So dg becomes dg is equal to vdp minus sdt. So from here we can write, for reversible isothermal process, dt is equal to 0, we will get dg is equal to vdp. So v is equal to partial differential of g with respect to p at constant t, and for reversible isobaric process dp becomes 0, so we can write s is equal to minus partial differential of g with respect to t at constant p. So we see that s and v are derivatives of g, and this fact implies that G is a thermodynamic potential. Now we discuss significance of thermodynamic potentials. First we take internal energy. Now at constant volume dV becomes 0, hence from first law we will get dQ is equal to du. Now the specific heat at constant volume is defined as Cv is equal to del Q over del T at constant V. So we can write here Cv is equal to del U over del T at constant V, because del Q is equal to del U. Hence specific heat at constant volume can be defined in terms of internal energy. This is the significance of internal energy. Second, we take Helmholtz potential or Helmholtz free energy. From first and second law of thermodynamics, we have du is equal to tds minus dw. Now for isothermal process, we can write tds is equal to d of ts. So above equation becomes du is equal to d of ts minus dw, or d of u minus ts is equal to minus dw. Now u minus ts represents F, so we can write dF is equal to minus dW. Hence the significance of Helmholtz free energy is that its decrease represents mechanical work available from it in a reversible isothermal process. This is why Helmholtz term it as free energy of the system. Now we see the significance of enthalpy. As we have H is equal to U plus PV, so dH is equal to du plus pdv plus vdp. Now putting the value of du here, we get dH is equal to tds minus pdv plus vdp. pdv cancels, we are left with dH is equal to TdS plus VdP. So at constant pressure we will have dP is equal to 0. So above equation can be written as dH is equal to TdS. But TdS is equal to dQ from second law. Therefore we have dH is equal to dQ. Now the definition of specific heat at constant pressure is Cp is equal to del Q over del T at constant P. We put the value of del Q is equal to del H here. So we will have Cp is equal to del H over del T at constant P. This is the definition of specific heat in terms of enthalpy. The other significance of enthalpy is in connection with a throttling process in which Joule-Thomson effect takes place. A throttling process consists in the expansion of a gas through a porous wall. In this process, the enthalpy in the beginning and at the end of the process are equal. Now we look into the significance of Gibbs potential. Consider reversible isothermal isobaric process. From first and second law, we can write du is equal to TdS minus dW. That is du is equal to TdS minus PdV minus dA equals d of Ts minus d of PV minus dA, where dA represents the work done by the system other than the mechanical work done, which is PdV. Hence we have du minus d of Ts plus d of PV is equal to minus dA, or d of u minus Ts plus PV is equal to minus dA. But u minus Ts plus PV represents G, so above equation becomes dG is equal to minus dA. Therefore the significance of G is that decrease of G represents work other than mechanical work available from the system in reversible isothermal isobaric process. Another significance is that in isothermal isobaric process, dt is 0, dp is 0, so dg becomes 0. Hence G is constant in this process. This function G is particularly important in connection with the processes involving a change of phase. Sublimation, fusion and vaporization take place isothermally and isobarically and can be conceived as occurring reversibly. Hence, during such process, the Gibbs function or Gibbs free energy of the system remains constant. So here I conclude my lecture on thermodynamic potentials. I hope this will of some help to you. Thank you very much for listening. Thanks.